Okay, thank you. So my name is Microbial Dinka. I'm a senior R&D engineer for Pall Aerospace. And today I'm going to give you a presentation on the history of cabin air filtration and cabin air development, which starts in the early 70s with the introduction of the recirculated air in the aircraft. And the reason for that is the energy crisis and the demand for fuel efficiency. Now, originally, the filter were introduced to actually protect the recirculation filter from contaminants and also smoke. I remind you that as crazy as it may sound now, smoke was allowed in the aircraft. It was only banned in the early 2000s. Now, in the early 80s, the cabin crew were the one who raised certain complaints about the microbial loading and microbial and bacterial loading. And so in the early 80s, Air France, and now Air France, back in the days, Inter, approached Pall and they started the development of what we call now HEPA filtration. These filters were validated for microbial protection in the late 90s, and again they were introduced in the 2000s. Following on that, as I mentioned, the smoking was banned in the early 2000s, and that unfortunately unveiled another problem. Which is the odors in the aircraft cabin, which it can be, odors produced inside the cabin or outside the cabin. The analogy that we like to use is, here in UK, for example, when smoking was banned in the pub, you could actually smell all the, carpet fibers and the nasty smells that were otherwise masked by the cigarette smell. And of course, from the early 2000s, when we introduced a VOC stage to this HEPA filter, we've been continuously looking at improving the performance, looking at new materials. And I recognize some of the names, and I know some of you have background in airspace and aircraft filtration, but hopefully by the end of this presentation, the people that are not so familiar, we have a good understanding on how the ECS works, the environmental control system, and all the work that's been going on and put into this recirculation filters. A little bit about our initiatives in cabin air filtration. So we have a big strategic initiative within our company now that we call Pure Cabin. And this entitles 2 areas looking at Pall Clean Air Technology. We already have what we call ACAF, Advanced Cabin Air Filter for Recirculation, which includes particulate filtration and VOC, activated carbon. I'm going to go into a little bit more details about that. We also have Cockpit filters for some of the Boeing aircraft that entitles only activated carbon, so only VOC protection. And we're also working on mist and VOC eliminator, what we call MAVE, for fresh air filtration in the aircraft. We also have different initiatives regarding the sensing in the aircraft. We have some projects looking at bleed air sensor, but also cabin air sensors. I'm going to go into a little bit more detail on the aircraft's environmental control system. Thomas mentioned a few things on the percentage of recirculation air and what type of air we get in the aircraft. You need to, I was saying that the air coming from the engine is a high pressure and high temperature, and it goes through this air conditioning unit, ACU, in order to be conditioned to the right temperature and pressure to be fed into the mixing unit. From the mixing unit, the air passes through the cabin once before it reaches the HEPA and VOC filter, which we call the recirculation line. As 50% of the air is being recirculated and passed through these filters and into the mixing unit, and 50% is dumped overboard. Now, the fresh air, there are a lot of regulation regarding to the fresh air and the ECS. The main purpose of the recirculation air is to regulate the temperature and the pressure into the cabin, also to disperse carbon dioxide and increase humidity. We know that in cruise the humidity outside is very low. And so typically in cruise, we get 15 to 20% RH in the cabin, but most of that comes from the recirculation air. Also, the fresh air is regulated, currently to 0.28 meters cubed per minute, or 10 CFM per person. And the air in the cabin is actually changed quite often, every 2 to 3 minutes, the air is changed within the cabin. So from that point of view, compared with other environments, the cabin air quality can be considered relatively good. A little bit about the filter and the recirculation air itself. You can see on the left-hand side the actual ECS. So you're looking at the mixing chamber, and on each side of the mixing chamber we have this recirculation line. The two filters on top, you see there are cylindrical filters typical for A319 2021 type of architecture. We see the two recirculation fans, and on the top of the mixing chamber, we see the distribution ducts. So there are 5 distribution ducts in total. The 2 that you can see on the top of the mixing chamber are feeding the forward cabin. There are 2 that you can't see that are feeding the aft cabin, and also Cockpit airline, which feeds the cockpit filter only. On the right-hand side, you can see an example of the cabin air filters that Pall distributes. So you can see a square configuration, which can be an aircraft Airbus A330, 340, for example. And as I mentioned, the cylindrical one, which is typically A319, Airbus A319, A320. Going into a little bit more details about the filtration itself. So I've heard some people in the audience talking about aerosols and particles, which is good, because I know some of the audience that might be familiar with this. So when we talk about HEPA filtration, we talk about three main ways of filtration. One would be direct interception. You can see illustrated these different methods on the right hand side. So we have direct interception. This is where the particle is bigger than the distance between 2 fibers. So it's just too big to go through the gap. The second one is inertial impaction. This is where the particle travels through the depth of the media and is caught on the surface of the fiber. And the third one is diffusional interception. This is mainly applicable for very small particles. And the smaller the particle, the more the particle will behave like a gas. So if you think about Brownian motion, for example, the particle would behave in a chaotic mode, and it will eventually impact on the fiber. Now, how do we translate that into removal efficiency or HEPA efficiency? Well, if you look on the graph, we have 2 representation depending on air velocity. We have 5 centimeters a second and 2.5 centimeters a second, just to show you how the efficiency varies with the velocity through the media. And these are typical for 5 centimeters per second, for example, is quite typical of a HEPA filter that is used in an aircraft. So these are actually efficiencies that of the filter that will be fitted to an aircraft. And of course, we know a lot of the standards. The one that it's very referenced at the moment, especially if you work in HEPA filtration, is EN 1822. Which is giving you a rating based on the most penetrating particles. So you would hear about H13, H14. And for these ratings, we're looking at different removal efficiency. So for example, you will see that H14 rating would require a minimum efficiency at the most penetrating particle of 99.995. Whereas H13 rating would require a minimum efficiency at the most penetrating particle of 99.95. So usually for HEPA filtration, the most penetrating particle would occur around the size of 0.1 to 0.3 microns. And based on the three different mechanisms that I've explained, you can see that as the particles, as the size of the particles increase, so does the efficiency when we're looking at the particle size bigger than the most penetrating particle. This is on the right-hand side of the graph. And subsequently, on the left-hand side, when you are looking at particles that are bigger than the most penetrating particles, so bigger than 0.1 microns, you can see that the efficiency increases again, because that diffusion interception mechanism takes takes part, and the particle are behaving more like a gas. And of course, I should mention that with the current COVID-19 situation, we get a lot of inquiries on very very blunt questions such as how efficient is your filter at removing COVID-19? And of course, it's not as easy as just saying a number. You have to look at these kind of graphs. You have to have a certain particle size in mind, and using experimental data and also the theory, you can give a rough answer, but it's not always as easy as just saying my filter is 99.95 efficient with COVID-19, etc. And yeah, this is what I mentioned before as well. So for a HEPA filtration, for a HEPA filter, in order to be classed as HEPA, you need a 99.97% efficiency. We tested with DOP, so dispersed oil particulate. If you're testing with a sodium chlorine challenge, you need a 99.99, and the reason for that is because the chlorine soda particles are bigger than the DOP challenge. So it's 0.5 microns for sodium chlorine and about 0.3 with DOP. And in the table you can see summarized kind of what I've said before. If we get very direct questions on coronavirus, SARS, MERS, how efficient are you at removing these things? And based on the virus approximate size, we can go back to the graph I show and say, if your virus approximate size is between 0.08 and 0.16 microns, then we could expect 99.993 removal efficiency. On the left hand side as well, in the picture you can see how the air is actually distributed in the cabin, and this is particularly helpful because it will not allow the circulation of the air vertically through the cabin. Rather, it will create a circle from the distribution, which is at the top of the cabin, to the exit, which is at the bottom. And this is also being sustained by very recent studies on the infection with COVID-19 or other infection diseases, where you are very likely to catch an infectious disease while people that are sat next to you, but it was very unlikely that this infection would travel, across the cabin environment. Now I'm gonna go ahead and talk about the VOC part of the filter. So we use an activated carbon downstream of the HEPA pack in order to catch the odors in the cabin generated within the cabin, or from ingested through the ECS from the outside environment. And of course, there's different ways that you can pack this technology. You can use a packed bed. You can have a pleated activated carbon cloth. However, because of the restrictions that we have in the ECS concerning flow pressure drop and also a space, excuse me, the technology that we use is a carbon foam pad that you can see on the left-hand side at the bottom of the slide. And the advantage that we have using this material is that we have a minimum pressure drop, which also helps with the life of the HEPA pack. And just a few fundamentals of the adsorption mechanism, although I'm sure some of you might be familiar with this, is a mass transfer zone. So in most absorbents, the mass transfer zone would occur at the top of the adsorbent, and this would result in a certain efficiency that would start with at the beginning of the life of the adsorbent. So we will usually start with 100% efficiency, and as the mass transfer zone travels to the depth of the adsorbent, and it will go on the other side, what we call breakthrough, then we are starting to slowly decrease that efficiency and get to the end of the life of the adsorbent. And this is very important for us to understand also how these filters, how this activated carbon foam filter that we have in the aircraft, to understand its behavior and its life. And in terms of capacity of the carbon, we also know that it would only adsorb preferentially certain compounds based on their boiling point or mass. So on the left-hand side, you can see some analysis that we did on the actual return filters from service. And usually the rule of thumb that we use is that if you want to adsorb a compound on the activated carbon filters that we provide, you have good chances of doing it if the boiling point is above 50, and very good chance of doing it if the boiling point is above 150. On the right hand side, you can also see some of the testing that we did by feeding a cloud of VOCs, so a mixture of VOCs, and it's showing a very similar trend. The molecular weight being related to the VOC point, we see the same trend. As the molecular weight increases, so the relative mass retained, or the capacity of the material to retain that particular compound. In terms of evaluating performance, what we do is on different platforms like Airbus A320 and Airbus A330, we work closely with both with OEMs but also with airlines, and we're very interested in evaluating the performance of this filter with real life contaminants. The issue that we have, and most of the people that want to qualify these type of filters, is that it's very difficult to have a standard way of testing and evaluating these filters in the laboratory environment, because we will never be able to replicate the type of contaminants and the type of concentrations that we find in the aircraft cabin. And so the best way of doing this is to get filters back from service at different intervals of time and evaluate their remaining life, but also trying to find out what the filter absorbed. So starting with the first one, what we do is working closely with airlines. We receive this filter from service and we challenge them with 3 different contaminants for what we call a spot efficiency. So you will see the 3 band lines correspond to 3 different contaminants. So the red line corresponds to toluene, the green line to limonene, and the blue one to dodecaine. So what this tells us is that for different type of contaminants, we get a different type of life. We get questions from customers like how efficient is my filter after 2,000 hours, for example, and it's not as straightforward to answer that question, because we need to ask ourselves with what contaminant. If you look at toluene, you're probably at the end of your life, because the boiling point is so much lower than limonene and subsequently dodecaine. If your challenge is limonene, then you're a very good chance of being 50% efficient. If you're looking at dodecaine, then actually your filter is performing quite well. If you look at the graph on the right hand side, it's A330, we're seeing a similar kind of trend, but somehow a better performance. So if you're looking at 2,000 flight hours, an A330 filter would have a better efficiency for toluene, limonene, and subsequently dodecaine. And the reason for that is purely because the depth of the adsorbent is twice for A330 than it is for A320. So thinking back of that graph of the mass transfer zone that I've showed you, because of the mass transfer zone for the A330 is twice that for the A320, we see that in the performance of the filters that we receive back from service. So this is the first type of test that we do on the filters that we receive back from service. The second analysis that we do is GCMS. So we send samples to an outside lab, and what they do is they perform a GCMS analysis in 3 steps. The first step is they take the filter to 120 degrees C, so thermal desorption 120 degrees C, and they capture the compounds at that temperature. The second one, on the same sample, they raise the temperature to 280 degrees C and capture the compounds and analyzes through MS. And the third type of analysis on a different sample from the same filter, they do a CS2 carbon sulfide extraction, which is meant to really take out all those compounds with a high boiling point that were not able to be analyzed through the thermal desorption at 120 and 280. And so we get a big table with all these compounds and their subsequent concentrations. And having analyzed, a lot of filters to date, we see this trend. We see that most of the time, the bulk of the compounds that is absorbed by these recirculation filters are compounds that are generated within the cabin. So we see a lot of siloxanes, we see a lot of dodecaine, most of them coming from cosmetics, hairspray and clean products, personal care products. But we also see type of compounds like dodecaine or TBP, tributyl phosphate, or toluene, which can be associated with aircraft engine exhaust, plasticizer, type of contaminants that are most probably coming from outside of the cabin. They're not generating inside the cabin. Again, another analysis of the filter. So in this case, we're looking at a filter with approximately 4,000 flight hours. So it's very close to the end of its life. And you can see that 40% of the compounds, 42% of the compound is represented by ethanol. But again, we have 20%, 3%, another 3% represented by siloxanes and limonene. Again, we see compound number 7 is TBP, tributyl phosphate, which can be attributed to aircraft hydraulic fluid. In terms of VOC adsorbent deactivated carbon by boiling point, we also see this interesting trend, which can be associated back with the mass transfer zone that I mentioned before. Each compound having a different mass transfer zone depending on boiling point. So when we analyze filters with a lower flight hours, so if you look at 330 flight hours, for example, we see that the difference between VOCs with a lower with a boiling point lower than 150 C and higher than 150 C are not as different compared with the total. However, if we look at the trend and the filters coming back after 1,000, 2,000, 3,000 flight hours, we see that the bulk of the VOCs absorbed by the carbon are actually represented by VOCs with a higher boiling point, so anything above 150 degrees C. And this is something that we would expect is a natural thing that happens with absorbents, that some VOCs are preferentially absorbed to others. But it was interesting for us to find this out and understand how the filter behaves throughout its life. I mentioned that when we get these filters back, the recirculation filters, we get a mixture of aircraft cabin air contaminants and outside contaminants. However, what you can see on the right hand side bottom picture there is a cockpit filter from a DHL aircraft, so no passenger aircraft. And what we are able to differentiate and to see when we did the same GCMS analysis on this filter, is that we are only able to see the outside environment contaminants. So we've taken out the cabin air and all the cabin air contaminants and all the the volatiles that are produced or that are coming from the people, and we're only able to zoom in and see those contaminants coming from outside. So in this case, when we did the GCMS analysis, you see that the bulk of the contaminants are represented by aircraft engine exhaust related, component of hydraulic fluid, jet fuel component. So we're looking at toluene, we're looking at TBP, benzene, MP-xylene, a few siloxane as well, but you can definitely see the difference between the type of contaminants that are absorbed by a cabin air filter and the type of absorbents that are absorbed by a cockpit air filter that's only seeing contaminated air from outside. With this, I am finishing the presentation and I will take any questions.